Hey everybody, how's it going? Today we're going to do a quick problem of Coulomb Mohr theory and modified Mohr. If you're in machine design, this is something you're going to have to know. So here's the problem. The counter shaft shown has two support pulleys. T2 is 15% of T1. The material we're using is ASTM number 50 cast iron, which you can find in machine design textbook tables. Uniform diameter for static analysis of the side where do the static analysis on the side where sigma x is in tension, which means on whichever side of the shaft here, the sigma x will be in tension so that it will be a positive. I'll show that a little bit later. So plot the shear moment diagrams for the x, y, and z planes, and then find minimal allowable diameter size for the nearest millimeter using Coulomb Mohr theory. If a factor of safety is 3.0 is to be maintained, and then repeat that with modified Mohr, and then talk about the results a little bit. All the dimensions are in millimeters. Okay, so here's our thing, our design here. We've got two pulleys. This is off at a little bit of an angle, 45 degrees. Spacing is 300, 400, and then 150 right here. I'm reading these off because you guys might not be able to see it, and there you go. You guys can get the numbers off of me. Okay, so first thing I did was I did a basic three-body diagram, plotted all the reactions. I turned the angled pulley equations, or tensions, into the direction. The T here is actually a combination of T2 and T1 as shown over here, so T is T1 plus T2. But they're both going in the same direction, so I can say that. So I'll be able to direct those into the X or Y and Z directions, and then went through and then added this one up, which is 50 newtons plus 270 from up here, as you can see. And then the reactions over here at this bearing. And then just to make it a little clearer, I put the torques down here. I know that TA has to be opposite to TB, so I did it, set it up like that. And then in order for TA to be opposite to TB, I can tell that, or T1, yeah, TA opposite to TB. I know that T1 has to be greater than T2, so that's an assumption you can make, because if T1 is pulling harder, then it's going to rotate this pulley around like this. But if T2 is greater like this, then it's going to rotate the same direction as this TB right here, so it's not going to help you at all. So moving on with that, what I got done is I did the force equations already, and there they all are. You do the sum of forces in X, sum of forces in Y, some of the moments about Z, some of the moments about Y, and then the sum of the moments about X, or the sum of the torques, which will be able you then find T1 and T2 from some of the torques, and then you set that back up into MY, and then back up into MZ, and then back up to FY, and then back up into FX, and you get your reactions. I don't want to go through that because that's basic static, so everybody can figure that out. Basically, the total T is 370, and then you guys can pause this video and look at these equations if you have any questions about how that is all done. So, moving on from that. We have to plot the shear and moment diagrams. So I'm going to set this part over here, actually, so you can still kind of see it. But, okay, so the shear moment diagrams, I'm going to do it in the XY plane first. So, the shear is like this. Just do a basic plot here, just like this. So I know that the reaction at O in the Y direction is going to be negative 163. Well, actually, here, let me get this set up here. So this is at a distance of, what was it, 300 millimeters. And then this is moving on 400 from that, so 700 millimeters. And then 150. It's not really to scale, but you guys get the idea. And then right here we have reaction OY. And then we have T sine of 45. And then we have reaction of CY. In the XY plane, you can see it from right here. The XY plane, this T force doesn't have any effect, so we can just ignore it here on this shear moment diagram. Alright, so moving on from there. We know that RY is equal to negative 163, 153.41. And then we know that T sine 45 is 252. So adding that to negative 163, you go up here to 89.14. Like that. And then you know that's going to be constant all the way along there. until we get to shear, and then we know that RCY is equal to negative 89.4. So you know that your shear diagram goes to 0, so you know that works. You did your sum of the forces right, and it makes a nice pretty diagram. So then, doing the moment diagram for that same deal, 300, 700, and 150. Doing the moment in the XY plane. We start out with a moment of 0, but then we do the area underneath this shear diagram, which is going to be a negative moment. So we go down like that, and then finding that the area is equal to 163.41 times whatever that distance is, 300 millimeters. 300 millimeters. Okay, and then that will equal 49,023 Newton millimeters. You can see that? Cool. Alright, so we have this down here at negative 49,023 Newton millimeters. And actually, if I had done this, this is actually negative 163, so negative right there. So you know it's a negative slope, and you end up with a negative moment, so great. And then again, since you know it has to go to 0, you can just draw a straight line across from here. And you also know that this is all a positive slope, or positive value, so it's going to be a positive slope down here. And we're good, and you can make that assumption. And if you want to check, fine, but we already did the sum of the force equation. Okay, so moving on to the XZ plane. We start out basic shear diagram, 300, 400, 150. And you can see how these all line up. This just makes it easier doing the shear moment diagrams because you know which point it is all the time. So we start out with ROZ, which is 106. That goes over to there. Then we have the negative T cosine 45, which takes that down to negative 146.35. I know I'm going through this kind of fast, but you can get the basic idea of what happened up here and then just apply this down here with the new reactions. And this is a really long problem, so I don't want to create a terribly long video. So then going up here again, and then the new force of the T, the main force on this pulley over here, comes into play and shows up, and that takes it way up here to 173.45. 173.45. That's the addition of 140 and then 320, which is the force of the T, or the forces on this pulley over here. And then you take that over here, and then RCZ shows up, and it takes you down pretty close to 0. It's actually off by about 1, but it's close enough to 0 to be within rounding error. Okay, and then going on to the moment diagram here. This moment diagram actually requires a little bit more math than the first one, but moving on, anyway, we'll survive. This is actually in the X, and then this is in the Y, and then this is the moment diagram. Okay, there we go. So, the moment for the first one, we have a positive moment multiplied by the area, which is find the area under the curve. We find the maximum value for the moment. That goes up like this, and it is at 31,800 Newton millimeters. I know it's in millimeters. I'm sorry about that. I did that calculation earlier without rounding it up, but you can fix it a little later on in the problem because it's just the power of 3. So this could be 31.8 Newton meters if you want to do it like that. And then moving on to the next deal, we know that we need to find the area under this curve and then add it to that or subtract it from that because it's a negative area. And if you do that, you end up with a line that kind of comes down like this and goes down to here, equal to negative 26,740 Newton millimeters. I'll do that calculation for you over here. So, excuse me. So, 106 times 300 millimeters minus 140.35 times what is this? This area here, 400 millimeters. 400 millimeters, because that's the distance across here is 400 millimeters. And if you do that, you find out that it's equal to negative 267.40 Newton millimeters. So there you go. I don't know if you guys can see that. I'm sorry. It's tough to stand close enough, but yeah, calculation kind of goes maybe. Hopefully my camera focuses. There you go. I'm narrating. You guys know what's going on. And then again, you can do this area calculation over here and find out that the moment actually comes back up to 0. So there you go. So there's your shear moment diagrams in all their glory. You got the XY plane, the X moment diagram for the XY plane, and then the shear for the XZ, and then the moment for the XZ. Alright, awesomeness. So moving on from that, the next part we actually have to do is, I have to edit that out later. Next part we're actually going to have to do is stresses and shear, stress, strain, shear, all that stuff to find out exactly what the heck it is we're doing. So, in this case with the beam, the sigma x, which is this stress, is equal to the moment max times the radius of the bar over the moment of inertia. And then the shear stress, xy, is equal to the torque times the radius of the bar over j, and j is actually equal to 2I. J is a different kind of constant for shear stress, which is just kind of weird and a weird machine design concept. So let me fix my camera here a little bit. There we are. That should make it a little clearer for you. Alright, so sigma x. We know from our shear moment diagrams right here, we've got a negative 49 Newton millimeters, then we've got a 31 and a negative 26. So out of these moments, we know that negative 49.23 is maximum moment. So we're going to use that in our shear equation, or our stress equation here, which is then equal to negative 49.023 Newton meters. As you can see, I just converted the Newton millimeters to Newton meters here with this, just by moving the decimal point over a little bit. And then R is equal to D over 2, and we're trying to find D using Coulomb Mohr, so that's going to stay as it is. And then we've got pi e to the 4th over 64. And the reason it's pi d to the 4th is because I z is equal to pi d to the 4th over 64. Oddly enough. Now, moving on like that, this is equal to just using all the numbers we can and reduce this as far as we can. Do that with your calculator, you end up with negative 499.34 over d to the 3rd newtons per meter squared is equal to sigma x. So we got that. That's all happy. Okay, so then moving on to Tx, we got tau xy is equal to the torque. The torque we found out earlier, if you look at the stress strain that we did, the torque is actually equal to, excuse me, is equal to 33,000 Newton millimeters. So it's going to equal to 33 Newton meters. And again, d over 2 over j times, which is equal to IV times 2. So it's just basically 2 up here, and so that turns into 32. So it's pi d to the 4th over 32, which equals 168.07 all over d to the 3rd newtons per meter squared is equal to tau xy. Underline those because you're going to use them here. Alrighty. So, moving on a little bit now. Now we actually have to do the principal stresses. So, in order to use Coulomb Mohr. So, we're going to call it sigma A, which can also be sigma 1 if you want to, is equal to sigma x over 2 plus the square root sigma x over 2 squared plus tau xy squared. Alright, so yes, the stress equation is sigma A, as you can use sigma 1, 2, is equal to sigma x over 2 plus square root of sigma x over 2 squared plus tau xy. So there's normally a sigma y included here, plus sigma y and then minus sigma y. But in the plane stress diagram, sigma y is actually equal to 0, so we're going to ignore that. So sigma y is equal to 0, which allows this equation to reduce to this. So then using sigma x, excuse me, we end up with 499.34 over 2d cubed, this is negative, plus all this stuff over here, and then moving on, which then goes to equals negative 249.67 over d3, 249.67, 249.67, sorry about that, plus square root of doing all this math up here with the numbers that we had earlier, 62335.11 all over d to the 6 plus 28247.52 all over d to the 6. Okay, so that makes sigma a equal to negative 49.67 all over d to the 3rd plus, doing all this math in here, gives 300.97 all over d to the 3rd. You can just put that in your calculator and you'll get the answer out. And well, a little bit of mental math, but it's not the big of a deal. And then adding these two together is equal to sigma a is equal to negative 550. Oh, sorry. Moving on to sigma b already. That's not right. Sorry. Is equal to 51.3 over d to the 3rd. That looks better. Newtons per meter squared, because those are the units of stress. And if you go through the units here, you can see how they change. But the square root and all this other stuff, squaring going on, just makes units hard, so I kind of ignore them a little bit. So going on with that, and then sigma b, you can skip a few steps here because you know it's going to be almost identical, except this is going to be a minus sign. So then you've got negative 249.67, doing this reduction all the way down through there, over d to the 3rd, minus all this math in here, which remains the same again, 300.97 all over d to the 3rd. So then sigma b is equal to negative 550.64 all over d to the 3rd. And these are your principal stresses, this one and this one up here. Oops, sorry, totally didn't let you guys see that. So as I said before, reduction up here, going on, moving along like that, all happy times. And then bringing this number down here again, bringing that number down here again, and then just putting a minus in here. All the other math remains the same. And then you get your other principal stress. Alrighty, so now moving on. I'm going to start a whole new page here. So I'm going to go to the next page there, alright. Clean that all up. So, brittle Coulomb Mohr. Brittle, or Coulomb Mohr. Coulomb is actually an electrical scientist or physicist who did all this stuff. So some professors will pronounce it Coulomb or Coulomb, whichever one you want. Okay, so we're finding the diameter. As you could see in the previous chunk of stuff that we did, sigma a and b are in terms of diameter. So we're going to solve for the diameter now. We know that we have a factor of safety equal to 3. Diameter equal to question. Okay, and we saw earlier that the material was cast iron, so we know it's going to be brittle. So this is brittle Coulomb Mohr theory. You only use Coulomb Mohr for brittle materials. It's called brittle Coulomb Mohr, but sometimes you just call it Coulomb Mohr. Okay, so for cast iron, a few material properties of cast iron. These are coming from the Shigley book, Shigley Machine Design. E is equal to 100 gigapascal. So giganewtons per meter squared, which comes from table A5 in the back of the book. And then from A24, the ultimate strength is equal to 52.5 KSI. It's only in KSI, So you have to do conversion, which is equal to 3.62 times 10 to the 8th newtons per meter squared. And then SUC is equal to 164 KSI, which is equal to 11.32 times 10 to the 8th newtons per meter squared, which again is Pascals, or in this case it'd be almost gigapascals. You can't see that again. The camera's all out of focus. Sorry, I'm using a cheap webcam for this, so if you can't hear or see very well, I apologize. Okay, so moving on with that. Using the conditions of Coulomb Mohr, I'm not going to go into those, but we know that. Oh, excuse me. Actually, I'm going to go back to this sheet, this other sheet, to do this. So I know that sigma A is greater than 0, which is greater than sigma B. So within brittle Coulomb Mohr theory, this is case 2. So we'll be needing that here in a second, which comes over to here. And then in Coulomb Mohr theory, we see that within case 2, the equation is sigma A all over SUT minus sigma B all over SUC, which is equal to 1 over N, which is your factor of safety. I know I used FS up here, but it's interchangeable between N and FS. So then, plugging in all those numbers, we get 51.3 all over D cubed times SUT, which is equal to 3.62 times 10 to the 8th newtons per meter squared, minus, I'm sorry, I'm terrible at units. If you're another person who just doesn't care about units, then you will enjoy this. If you are someone, I don't usually use units very often in my calculations, except to keep something straight in my head. Units are really handy to solve a problem if you don't know where you're going, because they can kind of lead you to a solution, but in something this complex, they mainly just take up space, which is equal to 1 over 3. And this was SUC, which I got from the book. Okay, and then all this stuff solved down to 14.17 times 10 to the negative 8 all over D cubed plus 48.69 times 10 to the negative 8 all over D cubed, which is equal to 0.33. Okay, and then solving that out, 14.17 times 10 to the negative 8 plus 48.69 times 10 to the 8 negative 8 is equal to 0.33 D cubed. So I'm actually showing you the algebra on this because this is the important part of the problem. And then 190.48 times 10 to the negative 8 is equal to D cubed. So 0.012 meters is equal to D cubed. But we want it to the nearest millimeter. So it's 12.4 millimeters is equal to D. Sorry, not D cubed, just D. Alright, there we go. And if you want to round it up, that would be 12 millimeters is equal to D. So I'm going to use 12.4 just because that's nicer, and we actually need that in the next part of the problem. So that was brittle Coulomb Mohr. Now moving on to modified Mohr. In modified Mohr, the equation that you use is sigma B all over sigma A, absolute value. And then doing that calculation, I'm actually going to label this modified Mohr. Mohr went off by himself and figured this one out. So we're going to do that. So this is equal to negative 550.64 all over D cubed all over, that was sigma B, 51.3 all over D cubed. And now just by basic algebra, we know that those cancel and that one cancels. And then doing this math, this is equal to absolute value sign, big absolute value sign, is equal to 10.73, which is greater than 1, which now leads us to the modified Mohr equation that we're able to use, which is equal to SUC minus SUT times sigma A all over SUC SUT. I'll bring that up there a little bit so you guys can actually see it. Minus sigma B all over SUT. I know I'm switching between capital and lowercase letters on these, but A is A and B is B. We're not that specific with the variables in this case, so just bear with me on that. 1 over n. I'll say n right now, which is the factor of safety. So then, reducing all of this, we end up with big nasty thing. It is 11.31 times 10 to the 8 minus 3.62 times 10 to the 8. Oh my goodness, this is a hard one. And then sigma A is 51.3 all over d cubed all over 3.62 times 10 to the 8 of 11.31 times 10 to the 8 minus negative 550.64 all over d cubed all over 11.31 times 10 to the 8. And Newton per meter squared, just a E annoying there. And then 1 over 3, because we still have a factor of 62. Now, going through and doing all this stuff, we end up with 39.4.5 times 10 to the 8 divided by d cubed all over 40.94 times 10 to the 16 plus 48.69 times 10 to the negative 8 all over d cubed is equal to 0.33. Okay, and then solving this out, 9.636 times 10 to the negative 8 all over d cubed plus 48.69 times 10 to the negative 8 all over d cubed. Again, showing all my work here to you guys. Showed all my work in the rest of the homework problem. In engineering, it's very important to show your work because if someone can't understand it, especially your professor, they are going to yell at you and take points off. So do a good job on that. Show infinite amount of steps. And plus, when you come back and study later, it'll be a lot more helpful. 0.33. As you can see, these two powers are the same. They should be pretty close to the same so that you get a realistic number. If this one's way out of whack, then you may have missed like the 16 up here or the 8. I actually did this the first time I was working this problem. So just watch your powers of 10 up there. So we get 9.636 times 10 to the negative 8 plus 48.69 times 10 to the negative 8, which is equal to d cubed plus 0.33, which goes to 29.3 times 10 to the negative 8 plus 147.54 times 10 to the negative 8 equal to d cubed. And then solving that all out, you get 12.09 millimeters. There I skipped some steps, but they were shown in the last steps. You know what I all did, what we did. Okay, so that was the modified Mohr diameter. And from that, within this discussion, you can see that the diameter is half a millimeter smaller than the one we got from Coulomb Mohr, the standard Coulomb Mohr. So you can see that Coulomb Mohr is actually a more conservative theory because they require more material in order to stay within the same factor of safety, whereas modified Mohr gives you a little less leeway there, a little less material to work with because it's a lot more, it's a lot less conservative thing. It's a lot less conservative, so it thinks that you need less material for the same amount of strength that the Coulomb Mohr does. And there you go, that's modified Mohr in Coulomb Mohr. See you guys.